Example 11.5, Test of Independence. The test of independence is similar to the goodness of test. We will use the chi-square statistic, but there are differences, and the difference is at the degree of freedom. In the goodness of test, the degree of freedom is the number of categories, subtract 1. But in the test for independency, we want to find out the whether two variables are independent. So we have two category, okay, or two items that we're listing, and we will have I row for the first item and J columns for the second variables. So I'm going to show the example 11.5 to demonstrate. And the next thing about it is the expected value. We will need to use a contingency table for this to solve this type of problem. And the expected value will be the row total times the column total and divided by the sample total. So what do we mean by that? So in example 11.5, we want to see whether speeding violation is independent of cell phone usage. So we will have to refer back to table 3.2 in chapter 3 to understand this problem. So back to chapter 3.2, we are comparing, okay, if a driver use cell phone or a driver do not use the cell phone versus whether the driver have a speeding violation or the driver do not have speeding violation. So those are the two variables that we are testing, whether they're dependent. One is whether we use cell phone, that's one of the variables. And another one is whether they get a speeding violation. Now the total here and the total down here is something that we need to use to calculate the expected value. So what are those numbers? So in the table, it says the driver used a cell phone and has a speeding violation is 25 of them. And then 45 of the user that have speeding violation but did not use cell phone is 45. So altogether, 70 driver have speeding violation. And for the driver that use cell phone and have no violation, there is 280 of them, and 405 of them do not use cell phone and do not have speeding violation. And altogether, that row, okay, so this number is a row total because you add them up this way. This horizontally is a row, so you have 685. And column, you go down, you add it this way, okay? 25 plus 280 is 305. So this is the column total. So 450. And all together, okay? All together, you add 70 plus 685 or 305 plus 450. Altogether is 755, which is the sample total, okay? So column total, I use green to represent. So that is the observation. This is the observed value, okay? So O, or observed data. Now, we need to use this formula to calculate the expected value. So how do we do that? So I'm going to just write the same table. But then I'm going to write the expected value over here. Okay, so the expected value for the first cell. Okay, so this one right here. Well, use a formula. It tells us to use a row total. First row, right? So 25, you go follow the yellow arrow, you get 70 as a row total. You multiply by the column total, so you go down to the column, follow the green arrow, 305. And then you divide it by the grand total, 755. So you use a calculator, you get approximately 28.3. So for the next number, right? For the second number, you just do, so follow the yellow arrow, you get 70, and you go down. The green number is 450. So 70 times 450 and divided by 755, you will get 41.7. So you use this formula to calculate the expected value. You should get this. And you don't need to add them up, okay? Because horizontally, it should add up to 70 and 685. Vertically, so you're going down, you should get 305 and 450. And altogether, you add up the number, you should get 755. But what we need to use is the number in the middle because they are our expected value. So now, to calculate our test statistic chi-square, what we need to do, okay, use a formula. We add up the observed value, subtract the expected value, square, and then you divide it by the expected value. So what you do is the first shell, right? You have 25 as the observed value. Expected value is 28.3. You have to square it and divide it by 28.3. And the second shell, you get 45. Expected value is 41.7. You square it, you divide it by 41.7. And the third shell is 280. The observed value. Subtract 276.5. You square it, you divide it by 276.5. And the last shell is 405. So 405. Subtract the expected value, 408.3. Square divided by 408.3, the expected value. So you have 4 shells. You should add up 4 number. And then you will get the test statistic chi-square. It's approximately, so use a calculator, 0.7. Okay. So what is the test statistic of 0.7 tells us? So we have to draw a picture. Okay, so this is the chi-square distribution. What is the degree of freedom? So how many rows do we have? We have 2 rows, but we have to subtract 1 from it. Okay, times how many columns do we have? We're not counting all the columns in the original table. We're counting, okay, the cell, okay? There's only 2 columns for the cell. Either you use a cell phone or not use a cell phone. So 2 columns, you subtract it by 1. That is, you multiply them together, you should get 1. So the degree of freedom is 1. It tells us the mean is 1. And the test statistic that we get is 0.7. And we want to calculate the area to the right of 0.7. So just to go back, what are we doing right here? Okay, so just refer back our null hypothesis. We always assume, okay, the cell phone use, and so this is the first variable. The second variable is speeding violation. So we assume independent. So we assume independency. And we want to test the alternative is whether this cell phone use and the second variable, speeding violation, are dependent. Okay, so we assume independency. We test for whether there are significant statistical evidence that they're dependent. So we will have a degree of freedom 1 and a test statistic of 0.7. How do we know whether there's significant statistical significance? We have to refer to our test statistic and the chi-square table. So we have a degree of freedom equals 1, okay? And these are the number listed. We have test statistics 0.7, okay? So we pick this number, 2.706. So you draw the picture, you realize if we get a test statistic of 2.706, this area in the red is 0.1. And we also call this red region rejection region. Okay, but right now we have the blue area, we have 0.7. What the table tells us is that the p-value, which is the blue shaded area, is greater than the red area, 0.1. Now if you use our calculator, okay, so if you use your TI 83 or 84 and you follow the textbook, the test statistic you still get about 0.7, but you get a precise p-value for this test statistic is about roughly 0.4, which is true that is greater than 0.1. So what you can conclude is that because of p-value is greater than 0.1, we fail to reject the null hypothesis, or we would say no significant evidence that support our alternative hypothesis, which means they are dependent. Now, you need to be careful about this conclusion. When we fail to reject the null hypothesis, it doesn't mean that we accept the alternative hypothesis. Okay, it doesn't mean that the cell phone usage and the speeding violation are dependent. Okay, it's just saying that we don't have enough evidence to support it. Well, what we can do if we really truly believe that cell phone usage is dependent of speeding violation, we can do more testing. Okay, we can do more experiment, we can survey again, and we find out if that is truly no significant statistical evidence.